Good afternoon and welcome to the last talk of today's PyCon 2017. Before we start, I would very much like everyone who has a device capable of making noise to convince it not to do so, so that no one stares at you during the thing or mocks you on Twitter. The fire alarm is... everyone blames Sam for the fire alarm. That out of the way, I would like to introduce our speaker. Lynn Root is going to be discussing tracing and digging into your web services performance. Please make her feel welcome.
Hello. How are you folks? Good? Hyped up on sugar from all those donuts, right? At least I am. My name is Lynn Root. I am a site reliability engineer at Spotify. I also do a lot of open source evangelism internally, and you might also know me from PyLadies. If you haven't visited our booth, I think you are too late, unfortunately, but there's an auction tonight that you should all go to right after lightning talks. I want to quickly mention that I do have to run right after this talk to lightning talks since I am the chair. So if you have questions, you can walk with me really quickly. All right, to start off, quick question. Who has read the Site Reliability Engineering book from O'Reilly? Also known as the Google SRE book. Yeah, I see a couple hands. Maybe you can agree with me that basically the TLDR of every chapter is use distributed tracing. So with the prevalence of microservices where you may or may not own all the services, it's pretty much imperative to understand where your code fits into the grand scheme of things and how it all operates. So there are three main needs for tracing a system: performance debugging, capacity planning, and problem diagnosis, among some other needs as well. So while this talk will focus on performance debugging, these techniques can certainly be applied to other needs. Jam-packed day today, so I'll start off with an overview of what tracing is in the problem space. I'll also talk about general types of tracing that we can use, what key things to think about when scaling up to larger distributed systems. The inspiration for this talk actually stemmed from me trying to improve the performance of one of my team's systems, which implies that we don't really trace at Spotify. So I'll run through some questions to ask and approaches to take when diagnosing and fixing a service's bottleneck. And then finally, I'll wrap up with some tracing solutions for profiling performance. Again, I'm sorry I won't have much time at the end for questions, but again, you can walk with me. So in the simplest of terms, a trace follows a complete workflow from the start of a transaction or a request to its end, including the components that it flows through. So for a very simple web application, it's pretty easy to understand a workflow of a request. But when you add some databases, separate the front end from the back end, maybe throw in some caching, maybe have an external API call, and then all behind a load balancer, it gets kind of difficult to put together the workflows of requests. So historically, we've been focused on machine-centric metrics, including system-level metrics like CPU and disk space and memory, as well as app-level metrics like requests per second, response latency, disk writes, etc. And so following and understanding these metrics are definitely important, but there's no view into a service's dependencies or its dependence. It's also not possible to get a view of a complete flow of a request, nor develop an understanding of how one's service performs at scale. So a workflow-centric approach understands the relationships of components within an entire system. And we can follow a request from beginning to end to understand its bottlenecks, hone in on anomalistic paths, and figure out where we might need to add more resources. So when you look at a super simplified distributed system where we have a load balancer, a front end, back end, database, maybe an external dependency to a third-party API. So when we have redundant systems, it can also get particularly confusing to follow a request. How do we debug a problem of a very rare workflow? How do we know which component of this system is the bottleneck? Which function call is taking the longest? Or is there another app on my host causing distortion for machine-centric performance metrics, which is like the noisy neighbor problem, which is a growing concern as we all move to the cloud. So with many potential paths that a request can take, with potential issues at every node and every edge, this can be mind-numbingly difficult if we continue to be machine-centric. So end-to-end tracing allows us to get a better picture of these concerns. All right, so real quickly, there are many reasons to trace a system. The one that inspired this talk is basically performance analysis, trying to understand what happens at the 50th or the 75th percentile, or the steady state problems. We'll help identify latencies, resource usages, other performance issues. We're also able to understand questions or ask questions like, did this particular deploy of this service have an effect on latency for the whole system? Tracing can also clue us into anomalistic request flows, the 99.9 percentile. These issues can still be related to performance, but also help identify problems with correctness, like component failures or timeouts. Profiling, very similar to the first one, but here we're just interested in particular components or aspects of a system, and we don't necessarily care about the full workflow. We can also answer questions about what a particular component depends on and what depends on it, particularly useful for complex systems. And so when dependents are identified, we can actually attribute particularly expensive work, like if component A adds significant workload with disk writes to component B, which is helpful for attributing costs or just attributing blame. And then finally, we were able to create models of our systems and ask what-if questions, like what would happen to component A if we did disaster recovery testing on component B. All right, now on to tracing approaches. There are simple things that we can add to our web services, especially when you don't have any dependent or depending components that you might not have access to. Granted, you don't get any pretty visualizations or help with centralized collection beyond how you typically handle your logs, but you can still get a lot of insight. So this is an example Flask route and a decorator. Here you can simply add a UUID to each request received as they come in and add them as a header. And then log particular points of interest, like at the beginning and end of a request and any other in-between component or function calls. And then propagate those headers as you go on. And this is exactly what I ended up doing for my service, which made me scream for a better way, and hence this talk. I like to do a lot of conference-driven development. If your app is behind Nginx installation that you're able to manipulate, you can turn on its ability to stamp each request with a request or X request ID header, as you can see with the add header and the proxy set header. And then you can also add these to your Nginx logs as well. Next up, another approach. Black box tracing is essentially tracing with no instrumentation across components. It tries to infer workflows and relationships by correlating variables and timing with already defined log messages. So from here, a relationship inference is actually done via statistical or regression analysis. And the easiest way is with centralized logging, and if there's somewhat standardized schema to your log messages, so you can pull out some sort of an ID and a timestamp. And this is particularly useful if instrumenting an entire system is just too cumbersome, maybe too much coordination with engineers, or you can't otherwise instrument components that you don't own. And as such, it's quite portable and very little overhead, but it does require a lot of data points to infer relationships. It also lacks accuracy with the absence of instrumenting components themselves, as well as the ability to attribute causality with asynchronous behavior and concurrency. And Facebook and University of Michigan, they wrote a very readable paper about how they assessed end-to-end performance by employing essentially this method, and I actually have a link to it at the end I suggest reading. Finally, another approach to black box tracing, you can also network tap with the use of sflow or nfdump or like IP table packet data, which I'm sure the NSA is very familiar with themselves. One final common type of tracing is through metadata propagation. And this approach was made famous by Google's research paper on Dapper, which I also link at the end. Components are instrumented at particular trace points to follow causality between functions and components and services, or even with just common RPC libraries like gRPC, that will automatically add metadata to each call. And metadata that is tracked includes a unique trace ID, which represents a single flow, a single trace or a single workflow, and a span ID for every point in a particular trace. Like a request sent from client, a request received by server, or server responds, and then the span's start and end time. And this approach is best when the system itself is designed with tracing in mind, but who actually does that? And it also avoids the guesswork with inferring causal relationships. However, it can add a bit of overhead to response time and to throughput. So the use of sampling traces will allow you to limit that burden on a system and data point storage. So sampling between like 0.01% to 10% of requests can be plenty for understanding a system's performance. So when starting to have many microservices and scaling out with more resources, there are a few things to keep in mind when instrumenting your system, particularly with the metadata propagation approach. So things to keep in mind, I'll go into detail about each. We want to know what relationships to track, essentially how to follow a trace, and what is considered part of a workflow. And then how to track them. Constructing metadata to track causal relationships can be particularly difficult. There are a few approaches, each with their own fortes and drawbacks. And then how to reduce overhead of tracking. The approach one chooses for sampling is largely defined by what questions that you're trying to answer with tracing. And there may be a clear answer to sampling, but not without their own penalties. And finally, how to visualize. The visualizations needed is also to be informed by what you're trying to answer with tracing. So what to track? When looking within a request, you can take 2 points of view, either the submitter point of view or the trigger. So the submitter point of view focuses on one complete request, and it does not take into account any part of the request that is caused by another request or action. So for instance, evicting cache was actually triggered by request 2 in this example, but it's still attributed to request 1 since its data comes from request 1. And then the trigger point of view focuses on the trigger that initiates the action. So with the same example, request 2 evicts cache from request 1, and therefore the eviction is included in request 2's trace. So choosing which flow to follow depends upon the answers that you're trying to find, what you're trying to figure out. So for instance, it doesn't really matter which approach you choose for performance profiling, but following trigger causality will help detect anomalies by showing critical paths. All right, how to track, or essentially what is needed in your data, in your metadata. And what this essentially boils down to is it can be very difficult to track causal relationships within a distributed system. The sheer nature of a distributed system implies issues with ordering events and traces that happen across many hosts. There's often not a global synchronous clock available, so care must be taken when deciding how to craft metadata that is threaded through an end-to-end trace. So you can use a random ID like UUID or request ID header that I showed earlier, and it will help identify some causal related activity, but tracing implementations must then use an external clock to collate those traces. And then in the absence of a global synced clock, or to avoid issues like clock skew, looking at network send and receive messages can then be used to construct causal relationships. because you can't exactly receive a message before it's sent. However, this approach lacks resiliency, as there is a potential for data loss across external systems or from external systems, or just the inability to trace, to add trace points to components to components owned by others. Tracing systems can also add a timestamp, or timestamp from a local logical clock to the workflow ID, where it isn't exactly the local system's timestamp, but rather like a counter or some sort of randomized timestamp that is paired with the trace message as it flows through components. So with this approach, we don't need the tracing system to spend time ordering the traces as it collects, since it's explicitly in the clock data. But parallelization and concurrency can complicate understanding relationships here. And finally, one can also add the previous trace points that have been executed within the metadata to understand all those forks and joins, parallelizations, and concurrency. It also allows immediate availability of tracing data as soon as the workflow ends, as there is no need to spend time on trying to establish ordering of causal relationships. But as you can imagine, the metadata will only grow in size as the workflow progresses, adding to the payload. So basically, it boils down to this. If you really care about payload of requests, then a simple unique ID is your go-to, but at the expense of needing to infer relationships. Then you can add a timestamp of sorts to help establish explicit causal relationships, but you're still susceptible to potential ordering issues of traces if data is lost. And then you may add previously executed trace points to avoid data loss and to understand forks and joins and concurrency of a trace, while gaining immediate availability since causal relationships are already established, but then you suffer in payload size. And there's also the fact that no tracing implementation actually implements this last one. So end-to-end tracing will definitely have an effect on your runtime and storage overhead no matter what you choose. For instance, if Google were to trace all web searches, despite its intelligent tracing implementation with Dapper, it would still it would impose a 1.5% throughput penalty and add 16% to response time. So I won't go into that much detail, but there are essentially three basic approaches to sampling. There's headbase, which will make a random sampling decision at the start of a workflow and then follow all the way through to completion. There's then tailbase, which will make the sampling decision at the end of the workflow, implying some caching going on here. And tailbase sampling needs to be a little bit more intelligent, but it's particularly useful for tracing anomalistic behavior. And finally, unitary sampling, where a sampling decision is made at the trace point itself, and therefore sort of prevents the construction of a workflow. So headbase is simplest and ideal for performance profiling, and both headbase and unitary are most often seen in current tracing system implementations. And I'm actually not sure if there are any that implements tailbase sampling, unfortunately. All right, finally, what visualization you choose depends upon what you're trying to figure out. Gantt charts, quite popular, definitely appealing, but they only show like one single trace. And I'm sure you've definitely seen this type in your network tab of your browser dev tools. When trying to get a sense of a system's bottleneck, a request flow graph will show workflow that are executed, unlike Gantt charts, and can aggregate information of multiple requests of the same workflow. Another useful representation is a calling context tree in order to visualize multiple requests of different workflows. And this reveals valid and invalid paths a request can take, and it's best for creating a general understanding of system behavior. So the takeaway here is there's a few things when considering what we trace in a system, or when we trace a system. You should have an understanding of what you're trying to do and what you want to answer. What questions are you trying to address with tracing? And there's certainly other realizations and questions that might come about after tracing. For instance, with Dapper, Google is able to audit systems for security, asserting only authorized components are able to talk to sensitive services. But not without understanding what you're trying to figure out, you might end up approaching your instrumentation incorrectly. So the answer to this question will help identify what approach to causality that you take, whether it be trigger point or submitter point of view. Another important question, how much time can you put into instrumenting your system? Or can you even instrument all parts? And this will inform the approach that you can use to tracing, be it black box or not. If you can instrument all the things, then it becomes a question of what data you should propagate through. And finally, how much of the flows do you want to understand? Do you want to understand all the requests? Then you should be prepared to take a performance penalty on the service itself, and you can have fun storing all that data. Is a percentage of the workflow okay? If so, then how do you approach sampling? And that is answered in essentially what you're trying to know. So for understanding performance, head-based sampling is just fine. You also need to know whether or not you want to capture the full flow of a request, or if you only want to focus on a subset of a system, and this will also affect your sampling approach. And I'm just going to go ahead and answer this for you, because I'm up here. So with performance or steady state problems, you want to try and preserve trigger causality rather than submitter causality, as it shows the critical path to that bottleneck. And as I mentioned before, head-based sampling is fine, as we don't need intelligent sampling. And even with very low sampling rates, we can get a pretty good idea of where our problem lies. And then finally, a request flow graph here is ideal. Since we don't care about anomalistic behavior, we want information about the big picture rather than looking at particular individual workflows. All right, so most often when you're tracing a system, the problem will reveal itself, as will the solution. But not always, so I have a few questions for you to keep in mind when figuring out how to improve your service's performance. Are you making multiple requests to the same service? Round-trip network calls are certainly expensive, so perhaps there's a way that you can batch requests. Perhaps your service doesn't need to be synchronous, or it unnecessarily blocks. For example, if you're some big social network site, can you grab like a user's profile photo as well as their timeline data at the same time that you get their messages? And then is the data, the same data being repeatedly requested but not cached? Or perhaps you're caching too much, or maybe not the right data, or maybe you've set the expiration too high or too low. And then what about your site's assets? Could they be ordered better to improve loading time? Can you minimize the amount of inline scripts, maybe make them asynchronous? Are there a lot of distinct domain lookups that add time from DNS responses? Perhaps you can actually decrease the amount of actual files referenced or minify and compress them. And there's certainly a bunch of things that you can do with the front end. And finally, perhaps you can use chunked encoding when returning large amounts of data, or otherwise be able to have your servers produce elements of the response as they are needed, rather than trying to produce all elements as fast as possible. All right. So some systems and services that are currently out there. So impressively, there is actually an open standard for distributed tracing, allowing developers and applications or open source packages or services like Nginx or ORMs to instrument their code without vendor lock-in. And they do this by standardizing trace span APIs. The one criticism I have is that they don't really prescribe a way to implement more intelligent sampling rather than just simple percentage and setting priority. There's also a lack of standardization for how to track relationships, whether it be submitter or trigger-based. It's pretty much all submitter. So this is basically a standardization for managing the span itself. But mind you, it's still very young, ever evolving and developing. And there are a few self-hosted popular solutions that do support this open tracing specification. The one widely known, probably most used, is Zipkin, which is from Twitter. It has implementations in Java and Go, JavaScript, Ruby, and Scala. And the architecture setup is basically the instrumented app sends data out of band to a remote collector that accepts a few different transport mechanisms like HTTP, Kafka, and Scribe. So with propagating data around, all of the current Python libraries out there only support HTTP. There's like no RPC support. And then finally, with UI, Zipkin does provide like a very nice Gantt chart or a waterfall chart for individual traces. And then you can also view a tree of dependencies, but it's essentially a tree with like no information as to like latencies or response codes or anything else. So you can see dependencies and dependents, but nothing else. So using PyZipkin, on which a lot of other libraries are based, you need to define a transport mechanism, which can be just a simple post request with content. You can otherwise define a Kafka or a Scribe transport, but then it's just a simple context manager placed wherever you want the trace. Jaeger is another self-hosted tracing system that supports the open tracing specification, and it comes from Uber. So rather than the application or the client library reporting to a remote collector, it reports to a local agent via UDP, who then sends traces to a collector remotely. Unlike Zipkin, and Zipkin only supports Cassandra, or Zipkin supports Cassandra, Elasticsearch, and MySQL. Jaeger only supports Cassandra for its storage. The UI is very similar to Zipkin with pretty waterfall graphs and dependency tree, but again, no aggregated performance information. And their documentation is also very horribly lacking, but they do have a decent tutorial to walk through, because tutorials are always better than documentation. And then their client library is pretty cringeworthy as well. And I took this from their docs. This is a trimmed example, but you can get the gist here. Basically, you initialize a tracer that the open tracing library will use and create a span and child span with context managers. But their usage of time.sleep for yielding to IO loop is a bit of a head scratcher. Its docs also make mention that they support monkey patching for libraries like requests and Redis and urlib2. So all I can say is use at your own risk. There are a couple others. I didn't get a chance to play with them, including AppDash and Lightstep that both support Python, or both have Python client libraries. And then there are a few more that don't have Python client libraries quite yet. So in case you don't want to host your own system, there are a few services out there to help. There's Stackdriver Trace from Google, not to be confused with Stackdriver Logging. And unfortunately, Google has no Python or gRPC client libraries to instrument your app with. They do have a REST and an RPC interface if you feel so inclined to use that. But they do have support for Zipkin traces. So you can set up their own Google-flavored Zipkin server, either on their infrastructure or yours. And then have that forward traces to Stackdriver. And they actually make it pretty easy. I was able to spin up a Docker image and start viewing traces within a couple of minutes. And one last thing, it's kind of annoying. Storage limitation is set at 30 days, and it's similar to their Stackdriver logging service. Next up, Amazon. They also have a tracing service available called X-Ray. I was only able to set up their Node app, but it looks like they don't have explicit Python support. But there is the Python SDK Botto, and it has support for traces sending to local daemon. And then I'm running out of time. So what's nice about X-Ray is, despite it being proprietary and no open tracing compliant, you're able to configure sampling rates for different URL routes, but you can't with Botto, unfortunately. But their visualizations are awesome. There's a typical waterfall chart, as well as request flow graph to see average latencies, captured traces per minute, and requests broken down by response status. So essentially, AWS seems pretty cool, could be useful, but you'd have to spend a lot of time instrumenting your Python app, and it includes vendor lock-in. And a couple of honorable mentions. And then finally, a quick opinionated wrap-up. If you run microservices, you essentially need to trace them. Otherwise, it's very difficult to understand everything. But good luck. There's lots of lack of docs. It's a very young space, and the standard is still developing. And as I mentioned, there isn't 100% support for Python language. And there's a lack of configuration for relationship tracking, intelligent sampling, and available visualizations. But OpenSpec that you can influence, or you can implement your own tracing system if you're so inclined. All right, that is all. So thank you. All sources and links are on that link, and you can run with me to the lightning talks to talk. Thank you.
Thank you again, Lynn. And as has been mentioned, lightning talks are happening in about 10 minutes in Hall C. Thank you.